Hello, I am Avnish, and my presentation for my DA3 is the topic exploring the zero logon vulnerability. So, what is the zero logon vulnerability? ZeroLogon is a critical vulnerability in the Netlogon authentication process, a vital component of Windows environments. This flaw allows attackers to exploit authentication mechanisms, posing a significant risk to the security of network systems and the integrity of authentication protocols. It was discovered by Tom Turboot, a Dutch researcher working for Secura in the September of 2020. The vulnerability was actually patched in August, but it wasn't until the researcher published his report in September that we started to see proofs of concepts and other activity. ZeroLogon is a high impact vulnerability in the Netlogon authentication process, a crucial component of Windows environments. This flaw poses a significant risk, allowing attackers to exploit authentication mechanisms. Netlogon is a part of the Windows Server operating system and is responsible for various authentication and authorization tasks in a Windows network. Netlogon plays a pivotal role in the security of Windows networks, facilitating authentication and authorization processes. Understanding its significance is key to grasping the impact of the ZeroLogon vulnerability. ZeroLogon allows an attacker to exploit a flaw in the Netlogon remote protocol, which is MSNRPC, which is used by Windows machines to authenticate users and update passwords within a Windows domain. Let's get a deeper dive into what Netlogon is and how it works. The Netlogon remote protocol is an RPC interface available on Windows domain controllers. It is used for various tasks related to user and machine authentication, most commonly to facilitate users logging into servers using the NTLM protocol. One of its interesting uses is that it lets a computer update its password within the domain. It uses a customized cryptographic protocol to let a client and server prove to each other that they both know a shared secret. This shared secret is the hash of the client's computer account password. So, the details about this vulnerability. ZeroLogon is a purely statistics based attack that abuses a feature within MSNRPC. Microsoft uses AES CFB8 for a function called Compute Netlogon Credential. This function takes an 8-byte input and performs a transformation on it with a secret session key that produces an output of equal length. AES-CFB8 encrypts each byte of the plaintext by prepending a 16-byte initialization vector to the plaintext, then applying AES to the first 16 bytes of the IV plus plaintext, then taking the first byte of the AES output and XORing it with the next plaintext byte. This vulnerability is so dangerous it has received a 10 out of 10 for severity from the Common Vulnerability Scoring System or CVSS. Next slide shows the encryption diagram of this function. Here we can see that we prepend a random IV before the message is encrypted. When we perform AES encryption on it and we know the first two bits of the AES output, then we apply AES to the IV and only keep the first byte of the result. XOR this encrypted byte with the first message byte, this IV, and then apply again AES again to the 16 bytes IV and ciphertext preceding the next message bytes. We encrypt the next byte and keep going until the entire message is encrypted. When finished, we don't use the IV anymore, we throw it away. This function works perfectly fine. However, Microsoft hard-coded the initialization vector to use all zeros instead of a random string. When an attacker sends a message only containing zeros with IV of 0, there is a 1 in 256 chance that the ciphertext will be 0. This is the IV, and we are hoping that these first two bits will be 0. When an IV consists only of 0, there will be one integer 0 less than equal to x less than equal to 255, for which it holds that a plaintext that starts with n bytes with value x will have a ciphertext that starts with n bytes with value 0. This figure shows how this is possible. We assume that the IV is 0 and the message is 0. And since we are XORing 0 with 0, we will get the output 0. And this will continue until all of the steps are performed and we get the output as 0 again. So these are the steps of the exploit. First we spoof the client credentials, then we disable signing and sealing, then we spoof a call, then we change the computer's Active Directory or AD password, then we go from password change to domain admin. The first step, after exchanging challenges with a netter server rec challenge call, the netter stands for network. A client then authenticates itself by doing a netter server authenticate 3 call. This is the first step in the figure. Here we see that this challenge contains the following values: the domain controller or DC, the target device, also the DC in our case, and a nonce. In our case, this is the 16 bytes containing zeros. The third value means that for in 1 and 256 session keys, the correct client credential will also consist of 16 bytes of zeros. With this method, we can log in as any computer in the domain. This includes backup domain controllers and even the targeted domain controller itself. Next, while step 1 allows us to bypass the authentication call, we still have no idea what the value of the session key is. This becomes problematic due to Netlogon's transport encryption mechanism, which is RPC signing and sealing, which uses this key but a completely different scheme than the vulnerable compute netlogon credential function. Luckily for us, signing and sealing is optional and can be disabled by simply not setting a flag in the netter server authenticate 3 call. The server will receive the netter server rec challenge. The server will then generate its own nonce. This is called the server challenge, as we can see here, and send this server challenge back, which is the second step in the figure. Next step, spoofing a call. The client will compute its netlogon credentials with the server challenge provided. It uses the netter server authenticate 3 method, which uses the following parameters: a custom binding handle, and we will be using a package in Python called impacket, which does exactly this. Impacket handles this for us, it's negotiated prior to this. An account name, which is the domain controller's machine account name, a secure channel type, the computer name, the client credential string, and negotiation flags. All of these details have been mentioned in the Secura white paper. The plaintext password structure in the Netlogon protocol consists of 516 bytes. The final 4 bytes indicate the password length in bytes. All bytes in the structure that are not part of the password function are seen as padding and can have arbitrary values. If we simply provide 516 zeros here, this will be decrypted to 516 zeros, that is a zero length password. Turns out that setting empty passwords for a computer is not forbidden at all. So this means we can set an empty password for any computer in the domain, hence changing a computer's Active Directory password. The server will receive the netter server authenticate request and will compute the same request itself, using its known good values. If the results are good, the server will send the required info back to the client, which is what we see in the step 4. At this point, the attempt to exploit the ZeroLogon vulnerability is underway. The above steps will be looped through a certain number of times to attempt to exploit the ZeroLogon vulnerability. The actual exploit occurs at step 3 and 4. This is where we're hoping for the server to have the same computations as the client. This is where our 1 and 256 chances come in. The steps 1 through 4 have been shown in this diagram. Here we set the IV as 0. We get a server challenge. We remove the sign and seal. We get an OK. And then we set the encrypted password also as 0, as we have seen here. The final step. If the server calculates the same value, the client will re-verify, and once mutual agreement is confirmed, they will agree on a session key. The session key will be used to encrypt communications between the client and the server, which means authentication is successful. From there, normal RPC communications can occur. Now, patching and updates. Microsoft swiftly responded to the ZeroLogon vulnerability by releasing security updates. These updates address the specific flaws in the Netlogon authentication process and aim to prevent potential exploitation. The initial deployment phase started with the Windows updates released on August 11, 2020. These updates enabled the domain controllers or DCs to protect Windows devices by default, log events for non-compliant device discovery, and had the option to enable protection for all domain joined devices with explicit exceptions. Here, non-compliant devices refer to any devices which have this vulnerability enabled. The DCs were placed in enforcement mode, which requires all Windows and non-Windows devices to use secure remote procedure call or RPC, with Netlogon secure channel or to explicitly allow the account by adding an exception for any non-compliant device. Conclusion: the ZeroLogon vulnerability has brought to light the critical vulnerabilities that can exist within network environments, highlighting the need for robust security measures. This attack has had a huge impact. It basically allows any attacker on the local network, such as a malicious insider or someone who simply plugged in a device to an on premise network port, to completely compromise a Windows domain. The attack is completely unauthenticated. The user does not need any user credentials. The ZeroLogon's exploitations involves sophisticated steps from credential spoofing to changing a computer's AD password, emphasizing the complexity of the threat. Security awareness is paramount. All stakeholders, from system administrator to end users, must remain vigilant and informed about potential threats. These are the references. This is Secura's white paper on the original discovery of the vulnerability by Tom, and these are informational links about the ZeroLogon vulnerability and Netlogon. Thank you.